In the world of high-temperature industrial filtration systems, maintaining consistent airflow is critical to achieving production targets and emissions compliance. However, pressure drop, which is the reduction in pressure as gas flows through a filter, can fluctuate unpredictably, leading to reduced throughput, increased energy consumption, and premature wear on system components. These disruptions often go unnoticed until performance declines or maintenance costs spike. Understanding the root causes of pressure drop and implementing design and operational strategies to manage it can restore system stability. Ceramic hot gas filters, when engineered and maintained correctly, offer a robust solution by reducing thermal stress and enabling efficient particulate removal with minimal resistance. Optimized cleaning cycles, proper sizing, and balanced flow distribution are key to keeping pressure drop within acceptable limits. The design and configuration of the filter media are among the most influential factors in pressure drop. In hot gas filtration, ceramic and woven wire mesh filters are commonly used due to their structural integrity, corrosion resistance, and thermal resistance. However, finer mesh specifications or denser ceramic walls can increase flow resistance. Porosity, wall thickness, and surface area all play a role in determining how easily gas can pass through the filter, with lower porosity and thicker media typically resulting in higher pressure drop. As particulates accumulate on the surface of the filter, a cake layer forms, which adds resistance to the flow of gas. In ceramic filters, this cake is essential to capturing fine particles, but if not managed properly, it can harden or overbuild on the face of the filter, resulting in an elevated pressure drop. So pulse cleaning systems are designed to remove this buildup, but failure in solenoids, compressed air supply, or cleaning frequency can cause the pressure drop to creep up. Improper system design can lead to uneven gas distribution across filter elements, causing localized overloading and inconsistent pressure profiles. Factors such as duct geometry, nozzle plate alignment, and pulse tube configuration affects how evenly gas flows through the system. Poor design can lead to some filters working harder than others, accelerating wear and increasing differential pressure. The viscosity, density, and temperatures of the gas being filtered also influence pressure drop. High viscosity gases require more force to move through the filter media, increasing resistance. Additionally, sticky or condensable particles can form compacted cakes that are harder to clean, especially in systems without preheating or reagent injection. These conditions must be accounted for during system design and operation to maintain stable pressure levels. One of the most immediate consequences of rising pressure drop in a hot gas filtration system is elevated energy demands. As resistance builds across the filter media, fans or compressors must work harder to maintain the required flow rate. This increase in workload translates directly into higher energy consumption, often raising operational costs. Fluctuating or excessive pressure drop can restrict gas flow, reducing the overall throughput of the system. This not only affects production targets, but can also trigger shutdowns for cleaning and maintenance. In high temperature applications, such as those using ceramic filters, uneven flow distribution or hardened dust cakes can cause localized blockages, forcing operators to halt operations for inspections and remediation. These interruptions can cascade into delays for downstream equipment like turbines or reactors, which rely on consistent flow rates. Unstable pressure drop places additional stress on downstream components. Turbines, heat exchangers, and catalytic reactors are particularly vulnerable to flow inconsistencies caused by clogging or degraded filters. Over time, this can lead to erosion, fouling, or even mechanical failure. In systems where pressure drop is not properly managed, the increased turbulence and particulate reentrainment can accelerate wear on sensitive equipment, can lead to expensive repairs and replacements. High pressure drop can compromise filtration efficiency, allowing fine particulates or harmful gases to bypass the filter media. This can result in elevated emissions, risking non-compliance with environmental regulations. In industries where emission limits are tightly controlled, such as power generation or chemical processing, this can lead to fines, reputational damage, or forced shutdowns. Maintaining a stable pressure drop is essential not only for operational efficiency, but also for meeting regulatory standards. Preventing pressure drop begins with consistent and effective maintenance plans. In hot gas filtration systems, especially those using ceramic or wire mesh filters, routine cleaning is essential to remove accumulated particulate matter. Systems equipped with pulse jet or Venturi blowback mechanisms should be calibrated to activate cleaning cycles based on differential pressure thresholds. If standard cleaning fails to reduce pressure drop, a soak and backwash cycle using process-compatible solvents may be necessary to dislodge embedded contaminants. Proper sizing and media selection are crucial to minimizing baseline restrictions. Filters with balanced porosity and adequate surface area allow for lower face velocities, reducing initial pressure drop. Pleating or extended length cartridges can increase filtration area without extending system footprints. And in ceramic filters, uniform wall density and taper geometries help maintain laminar flow and prevent turbulence. And if the filter is not designed properly, it can lead to uneven cake formation and inefficient cleaning. Advanced filtration setups now incorporate automated cleaning systems triggered by real-time pressure sensors. These systems ensure timely removal of filter cake without interrupting interrupting operations. Technologies like Venturi pulse blowback allow for continuous filtration even during cleaning, maintaining consistent flow and minimizing downtime. Monitoring system log differential pressure trends can alert operators when cleaning cycles need adjustment or when filters approach the end of life. Stabilizing operating conditions, which can include gas flow rate, temperature, and composition, helps to prevent pressure spikes or drops. Sticky or condensable particles can form dense cakes that resist cleaning, so preheating or reagent injection may be necessary in some applications. Real-time analytics and predictive maintenance tools can identify patterns in pressure behavior, enabling proactive interventions before performance degrades. This data-driven approach ensures long-term system reliability and cost control. Thanks so much for watching. If you have any questions, click on our Talk to Us button to get in contact with our many experts on woven wire mesh. And if you'd like to learn more about woven wire mesh or our many products, we have a learning center filled with written and video content to make you an expert. We also have a YouTube channel. And don't forget to click that subscribe button and ring that bell to keep up with all things WS Tyler. Once again, my name is Andrew Kotlar, and I'll see you around in the next video. Bye for now.